Welcome to the examples video. So here is what we looked at previously, right? First thing you need to know is resonance. What does resonance mean? And how do the curves of resonance look like? If you have damping, light damping, critical damping, heavy damping, and things like that. So this is one curve we'll look at today. And another main idea for this unit is types of damping. Yes, we know damping. So this is two graphs you need to know lah, okay? This is from amplitude with respect to driving frequency. But then the other graph you need to know is displacement against time. So the sine graph and things like that. How to know the different types of graph and how to draw them and compare them. So go check out the previous theory video if you want to refresh this thing or I'm not very sure. So here today we are going to look at two examples. First one of the day is MJ10 Paper 4 Variant 2. So on page 5 you have the handout, but some parts of the question is chopped off in the handout, so maybe you want to grab a piece of paper and check out the full question. So what do we have here? A long strip of springy steel doing, 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 is clamped on one end so the strip is vertical. Mass of 65 grams is attached to the free end of the strip as shown. Okay, so this thing is gonna do some funny wobbly thing like that. Oh man, something like this. Okay, it's gonna wobble back and forth. But anyway, what's going on here? The mass is pulled to one side and released. Variation with T of the horizontal displacement is shown. So this thing. Is it damped? You look at the displacement, it starts off here, it gets smaller and smaller and smaller. Okay, so it's damped, so there'll be some question about that. The mass undergoes simple harmonic motion. Explain what is meant by damping. You need to know the definition for this, but hang on a second. Usually they will say define damping, but here they say explain. So you need to say what is damping and why is damping. So the best answer you can say is, well, what's damping? Damping is the reduction of or loss of energy due to frictional force and things like that. But anyway, the reduction of energy, or you can say amplitude also. Amplitude gets smaller and smaller. Then why does this reduction occur? That's the explain part. So why? You must include that. Due to, what's the thing called? Resistive forces or frictional forces. Resistive forces is the better term in the system. So resistive forces in the system. So in this case, what will be the resistive force? I don't know. Energy loss due to deformation of the wire, because you know you bend already, got some heat. I don't know. Air friction maybe. When you're moving in air, you get some air friction. So all these are possible forces, which they will sometimes ask you in past year also. Okay, 2 marks here. First one is what is damping? So that's this part. Second one, why is damping? So this one here, you explain. Okay. Now the next part is things you have to do with the graph already. First one, suggest with a reason whether your damping is light, critical, or heavy. Wow, so you have to remember how the graphs look like. And you see this one, it still go up and down, up and down, up and down, up and down. Still got a few oscillations. So it's probably light damping. But you need to describe that in words. So what you can say for 2 marks, suggest with a reason. So the reason I say light. But why do I say light? I need to say the reason. That's the 2 marks there. So I will say light damping as my choice. And I must give a reason because why? How to say? Many oscillation, amplitude decrease gradually. So I'm going to say that because amplitude decreases gradually. Gradually means slowly. It's not suddenly the amplitude becomes 0. No, that is other kinds of damping. So amplitude decrease gradually over time. And of course also there's still oscillation, so period is still the same. Or you could say there's many oscillations, it still go up and down a few times. Also can. But anyway, the main mark here is because amplitude decreases gradually over time. This is a M1 mark, gradually. And A1 for light damping. So if you just say light damping, you won't get any mark because the A mark is linked to the M mark. You must get the M to get the A. Method mark ma. Part B. Use the figure to determine the frequency of vibration of the mass. Frequency is F. How to find F? Oh, F equals to 1 over period. So you need to read what is the period of the mass. You say, Miss, if damping the period is different, right? No. When it's damped, the period is still the same. That's why we can say, oh, from here to here is a period. I mean, you can take other parts lah, but I'm going to say from here to here. So that's 0.3. Okay, so I'm going to say 0.3. 1 divided by 0.3 seconds. So that will mean my frequency is 3.3333333 hertz. It's fine. I'll just say 3.3 lah. Okay, 1 mark. Yeah, this is not AS anymore. If not, they may give 2 marks. Maybe. Okay. Hence is an interesting word. Means somehow you have to use the answer from part 1 inside this one. Hence, show that the initial energy stored in the strip before the mass is released is approximately 3.2 millijoules. So you need to show. They already give you the answer, so you need to figure out how to find energy before the mass is released. So when you bend it, this is supposed where it's supposed to be, but you bend it and then you hold it here. So it's some potential energy stored, and that is the total energy, which is also the kinetic energy when it's at equilibrium position. Go and review 13.2 and 13.3 if you feel like, I don't remember this thing. Go and check it out again. But anyway, maximum energy or total energy is also the speed. Okay, so the speed when it is at equilibrium, so V max lah, which is also the maximum potential energy. But we can't use Hooke's law because it's not exactly a spring. Anyway, so here, and we don't know what Vmax it is, but we know that the maximum velocity is related to amplitude times omega. Where did this come from? I'll go check 13.2, 13.3 again. We've learned this previously. So half m a omega square is the total energy or maximum energy of that steel strip. Let's plug in all the values. So half m is what? What is the m? We're going to look at this bobbing mass m, 65 grams. So our 65 grams would come down here. 65 must convert to kg, so this is in kg. A is amplitude. Have to read from graph, right? Initial energy stored. So initial means at the beginning. This is 1.5 right here. Right, we're here. Here. So that will be our initial energy, 1.5. Don't forget to square, yeah. 1.5, is that in cm? Yes, it's in cm. So must convert to meter. Times 10 negative 2. This is in meter squared. Omega, we already found previously. So that will be 3.33 square. Hang on a second. I see an error. Omega is 2 pi f, right? So you need to multiply 2 pi frequency, 3.33. This looks more correct. Okay, press calculator, everything. You should get about 3.2 times 10 to the negative 3 joules of energy. Is that correct? Yes, 3.2 millijoules, negative 3 milli. So where do the mass come from? First one comes from this line. Do you know what energy equation to use? So many energy, how to use? And then do you plug in the correct values? 2 pi f and everything. Okay, and if you get everything correct, okay lah, correct Eddie. Okay, initial energy, total energy. C. Ooh, this is the interesting one. After 8 oscillation of the mass, the amplitude reduced from 1.5 to 1.1. State and explain whether after a further 8 complete oscillation, the amplitude will be 0.7 or not. So how many oscillations on this chart? 1, 2, only got 2 here. How we can see 8? So this, you have to draw you have to understand how the graph of oscillation changes. So in a normal damped system, your amplitude will decrease exponentially one. So something like this. Can recognize the shape of the curve? It's like an exponential curve decreasing. So that means when you draw the oscillation, it's gonna have to follow, well, same period, of course, and then you have to do like that. The amplitude will decrease exponentially. But what did they suggest? 8 oscillation from 1.5 to 1.1. So that means 1.5 to 1.1. Okay. 8 oscillations later. 1.1 to... Will it be 0.7? I don't know. What is the factor here? Well, if you look carefully, they are saying after 8 cycles, your amplitude will decrease by 0.4, I think. Yeah, decrease by 0.4. Then they say, oh, maybe after that it decreased by 0.4 again. That is what we call a linear decrease. Linear scale. So if I draw it out, it's going to look something like that. 1, 2, 3, 4. Linear scale is your straight line graph, so like that. I try to draw a straight line graph. Straight line, yeah, like that. You see the difference? So here, if I draw the amplitude, it will be like that. Means after each cycle, it will decrease linearly by, I don't know, 0.8 cycles is 0.4, so each cycle it decrease a bit. There's a difference, okay? So this is exponential decay of amplitude. This is what we call a linear decay of amplitude, which is not correct. So how do we explain that? So we can say, amplitude decreases amplitude. That's more correct. Amplitude decreases exponentially. That's the word you want to use. Exponentially. Or non-linear lah. Okay lah, non-linear. Which they propose is negative 0.4 each time you decrease. No. That's linear. Non-linear. So it will not be 0.7 cm. Sure. After 8 oscillations lah. So your 2 marks here will be state and explain, right? So 2 marks, you state it will not be 0.7. That's your state part. So that will be your A1. But you need to explain. So in order to get that A1, you have to say, oh, it decreased exponentially, or non-linear. So this is your method mark. Okay, so careful what of this part. I think that's the end of this question. Okay. So that's the first one. They will ask you to explain things a lot. Calculation will be similar to the previous units. Another example you want to look at is on page 6, right after that. This is from ON10 paper 4 variant 1. This picture look very familiar, huh? This is a setup to test the the frequency response of the spring. So here you have an oscillator, and then on the other side a spring. So this oscillator is going to cause vibrations, and the vibrations will cause the spring to oscillate. You will see how later. The amplitude of the vibration produced is constant. The variation with frequency of the amplitude of the metal cube is shown. So this cube is going up and down at a certain amplitude. Okay, this is our resonance curve. State the phenomenon illustrated in 3.2. When you see this, you should already think of, resonance. So you just say resonance. You may say, Miss, why not damping? Cannot see damping. No. Damping is the graph we saw just now. Graph over time. You lose energy over time. But this is amplitude against frequency. So you're looking at a totally different phenomenon already. Resonance. Okay, so just write there resonance. Next one. For the maximum amplitude of vibration, state the magnitude of the amplitude and the frequency. So you're looking at maximum amplitude of vibration. So you look here. Where is maximum? Here, this peak here. And where does that occur? This will be 16, I think. And what is the frequency? Somewhere here. This is, wow, I cannot really see. 4.246. Because this is 5 already, ma. Okay, so we're going to write down what we see in the graph right here. So amplitude is 16, 2SF, okay lah. Frequency is 4.6. If you get both correct, give yourself an A1 mark for accuracy. Let's continue. The oscillations of the metal cube, 150 gram, may be assumed to be simple harmonic. Okay, we assume simple harmonic, which means all the equations for simple harmonic motion we can use now. For sure can use. Use your answers to determine for the metal cube the maximum acceleration. Whoa, what is maximum acceleration? For simple harmonic motion, acceleration is negative omega square x, but we can ignore the negative for now because we don't care about direction. So this is how we're going to start off with. But also, what is x? Where does maximum acceleration occur? I don't know. You look out and see. Maximum acceleration occurs when you are at the amplitude, or what the books call x naught. So we need to do that, x naught. Also, what is omega? 2 pi f, right? So you need to do 2 pi f square times your amplitude lah. So let's do the calculation. 2 pi frequency is what? Did we find the frequency yet? Have we found omega? Yes, we have. Previous section here. Frequency is 4.6. So let's use 4.6 here. Square times the amplitude, which is 16 millimeters. So 16 times 10 to the power negative 3. There we go. Okay, so multiply everything, you should get 13.37 meter per second square. Can round off lah, 13.4 or 13. I'll just put 13.4. 3 marks all. Where does that come from? First one, I believe, comes from your equation here. This one. Do you know how to find acceleration? Then you sub correct value, that's another one lah. Then the final answer here. Okay. Next, the maximum resultant force on the cube. Well, if you already calculate acceleration, then you can count the resultant force because you know the acceleration now. So, net force equals to, you can use a variation of Newton's second law to find the resultant force. So the mass is 150 grams, right? Yes, they give to us 150 kg times the acceleration that you found earlier. Wow, then before that wrong liao. Then you wrong here, your final answer, you will lose a mark. So let's use 13.4. And you get 2.01 Newton, which is also 2.0 Newton. 2 mark. Wow, very generous leh. 1 here, 1 here. Okay. Some very light feathers are attached to the top surface of the cube so that the feather extend outwards beyond the vertical side of the cube. The investigation is now repeated. On the graph just now, draw a line to show the new variation of frequency of the amplitude of vibration for frequency between 2 and 10. What feather are they talking about? Well, imagine this thing is going up and down, right? Now they go and put, I don't know, feathers like this, maybe, like wings. So what does that change? Not exactly the mass, but it does change how much frictional force this cube will be experiencing. Okay, feather ma, okay, the wind will blow against it. So we have damping now. That's what we call some significant damping. So how would you draw the curve? There are a few characteristics you want to take note. Okay, first thing is the amplitude will not be as big when there's damping. Okay, by the way, I'm going to draw this line here so we can see. So our peak has to be lower lor, so maybe something like this. And also, your line must be generally lower than the previous one. So the points come from, first one, if your line is below the original and never zero. That is the first mark. A second mark comes if your peak is at a slightly lower frequency at 4.6 Hz or lower, and flatter. The peak is flatter. So lower lor, flatter. So that's the two ideas you see. Before that, frequency is 4.6, but your new peak has to be at 4.6 or a little bit lower. So I prefer to do a little bit lower because once you have damping then your frequency will decrease a bit. So that's why I shift that. So you draw something like that lah. Okay, so that is the end of these two questions. Most of the others are very similar. Now before I let you go off from the example video, I'll do a very quick summary of the topics here that you should know and how you can apply to the real world for any kind of question that may throw at you. So next time, if you ever go to a park and then you have people doing their swing thing like this fella right here, okay, just keep in mind that eventually you will lose energy. So you see the amplitude becomes smaller and smaller and smaller. And you need to think about where is the energy being lost. Well, some places are friction. What other places? Oh, maybe you're moving, so you have air resistance. Many kinds of frictional forces. You need to be able to think about where they are. If you are in a fluid, liquid, there are some parts like that, then there will be, viscosity lah. Viscous forces, which is kind of also like air resistance lah. This is the mother of air resistance, drag force. Okay, so these are the talk about friction, why energy loss, where energy loss. You need to be able to describe that. Okay, and secondly, just remember that damping is about amplitude over time, which decreases exponentially. Or if straight away decrease, okay, decrease like that. That is critical damping or over damping. The second thing I want you to remember from this last part, before we wrap up chapter 13, is that there is now if you have a friend, or I don't know, somebody push you, or you push somebody on a swing, this is what we call a driving force right here. So this person pushing is pushing periodically. So this is called a periodic force. So you got some frequency with some frequency F, okay, driving force. And if you keep pushing at that frequency, then your system, which is the person on the swing, will have a very large amplitude, the largest possible ever. You guys know this intuitively because you played the swing before. But this is the science behind it. Driving frequency and driving forces lah, okay? So the driving frequency will cause you to have a certain response curve, and that is a different curve of amplitude against driving frequency. Okay, so this swing, depending on the length, will have a preferred natural frequency, like we talked about in all the previous videos. And if there's no damping, amplitude will be really big. Well, I didn't fly off the swing, so something like that lah, okay? So let's keep in mind these two ideas, resonance, driving frequency, and you'll be good for 13.4. Okay, so that's the end of 13.4. See you in the next section or chapter.